In the previous class, we were going through a worked example, and that worked example is shown here in this figure. We had a convergent divergent nozzle with the exit to throat area ratio being given, and starting from state 1, we evaluated the Mach number and the pressure, and for the ambient pressure, which was given to be 100 kPa, we noticed that for that ambient pressure the jet was over expanded, so oblique shocks are triggered. So we evaluated the state properties at 2, and then we also evaluated state properties at 3. Let me recap this, and after doing that we are going to evaluate state properties at 4, and that will terminate this worked example. So we are continuing the previous worked example. And if you recall from our last lecture, we evaluated the following things. M2 was calculated to be 2.5, P2 static pressure 2 was 50 kilopascal, and the static temperature T2 was 133 Kelvin, and the stagnation pressure P02 was 854.5. and the stagnation temperature was 300 Kelvin. So these were the flow properties that we evaluated at state 2, and for state 3 we calculated the state properties by noting the fact that state 3 is exposed to the ambient pressure. So the pressure here P3 has to be equal to 100 kilopascal. So that means we knew the pressure ratio and we knew M2. So this was somewhat unusual, because if you remember we said theta beta m relation. So given either m or theta or m or beta or theta and beta, any of the two, we could calculate the third one. In this case we are actually seeing that you are given the static pressure ratio and m2, and we are calculating theta and beta. So that is what we did. So P3 was known, so let us write that P3 was 100 kPa. And M2 was known, so we calculated M3 to be 2.04, and we calculated T3 to be about 164 Kelvin. P03 was evaluated to be 832.731 1 kilopascal, and T03 of course was 300 Kelvin. And if you recall, we calculated beta 2 to be 33 degrees, and theta 2, the flow deflection angle or the angle through which the jet is deflected, was calculated to be 11.2118 degrees. Now we wish to evaluate state properties at state 4, and before we do that we need to actually understand these angles very clearly. Let us draw an enlarged view of the jet as it comes out. So let us say that this is the exit and the fluid comes out like this. So this is a close-up view of the exit from the jet. We label this region as 2, and oblique shocks were generated from here, right, from the trailing edge of the nozzle. And this was labeled as region 2. Now if you look at the flow vector ahead of the shock wave, it looks like this. Remember, the direction of the shock wave itself in this case is like this. So after passing through the shock wave, the flow is deflected towards the shock wave by an angle of 11.2118 degrees. So that means the velocity vector in region 3 would look something like this. So the velocity vector looks like this in region 3, and this angle is theta. We calculated this as theta 2, and we said that the edge of the jet is going to look something like this, right? So this is the jet edge. Now notice that angle beta 2 is also measured with respect to the velocity vector ahead of the shock wave. So that means since the velocity vector ahead of the shock wave is like this angle is going to be beta 2, which is equal to 33 degrees, correct? Now, so when the flow goes into region 4, which is over here, which way is the flow going to be deflected? That is the first question. Remember, it is a shock wave, so the flow is deflected towards the shock wave. So what is the turning angle for this shock wave? What is theta for this shock wave? What is the wave angle for this, for region 4? Wave angle is measured with respect to the velocity vector ahead of the shock wave. So the velocity vector ahead of the shock wave is inclined like this. So that means the wave angle has to be measured. So this is the wave angle beta 3, correct? The wave angle is known. No, the wave angle is clearly known, and in this case we really cannot say that the flow is going to be deflected back to the horizontal. All we can say is that the flow is going to be deflected towards the wave. We know beta 3 clearly, so let us write beta 3. Right, beta 3 is known, so beta 3 is equal to beta 2 plus theta 2. So beta 3 is equal to, the value for this is going to be 44.2118 degrees. Remember, m3 is known, beta 3 is known. So we have to calculate theta from this relationship, see what theta is going to be. Whether theta is brought back to the horizontal or not is what we have to see. Okay? Are there any questions or doubts? Is this clear? Yeah, go ahead.
How come beta 3? We don't know beta 3, no?
We know beta 3 because remember, this is the wave angle beta 3, correct? This is the wave.
After intersection of two shock, there will be some other shock.
No. Remember what we said yesterday about intersection of shock waves. We said we are going to idealize this and treat this within the framework of our oblique shock theory. All we are saying is, if you look at this streamline, right? If you look at this streamline, it passes through the shock wave. It is deflected like this, and then after passing through this shock wave, it is going to be deflected back again like this, horizontal or this way towards this. So beta 3 for this wave is measured with respect to the velocity vector before that wave. Velocity vector before that wave is like this, so this is beta 3. And if I use the fact that this is beta 2, I can split this into two things. So this is my theta 2 and this is my beta 2. So beta 3 is equal to beta 2 plus theta 2. Okay?
But after intersection, direction of shock will be something different, no?
That is what I am. No, that is what I am saying. We are making an idealization that it does not change. Within the framework of what we are doing, we are assuming that the shock wave goes through without any changes.
Means flow is not parallel to original axis
Flow
after that shock.
Flow need not become parallel to the original axis here. Okay, intersection of shock waves is a much more complex phenomenon which we cannot deal with in our course. So what we are saying is we are neglecting any changes due to the intersection of the two shock waves. We are assuming that this is another shock wave. This will give us a very good idea of what is going on in such a situation. Okay, so that is an assumption that we are making, which I said even before.
If we assume the deflection angle as theta 2 equals to theta 3, then we can find out beta 3, na?
Theta 2, you do not know that theta 2 is equal to theta 3 because we know the Mach number here, okay, and we are saying that there is no change due to the intersection of the shock wave. So that means I know beta 2, this angle is known, right, this angle with respect to the horizontal is known. So I can calculate beta 3 much more clearly than, that is a much more general way of doing this than assuming theta 3 to be horizontal. But theta 3 will not be horizontal, some other process has to take place. This is a much better, within the framework that we are talking about, this is a much better way of dealing with this problem. Okay. The change in the wave angle due to the intersection of the shock wave is also not very large. That is well known from doing 2D calculations. So, this is a much more accurate way of doing things than assuming theta 3 to be theta 2. Yeah.
P4 equal to P ambient, then the theta 2 will be theta 3.
No, why are you saying P4 has to be equal to P ambient?
P4 is P ambient, then after all oblique shocks, and if the exit is P4 equal to P.
No, that is the whole point. The thing is, why did we say P3 was P ambient here? Because the fluid was in direct contact with the atmosphere, and the jet boundary cannot support a pressure difference. We are not talking about surface tension and so on. So, you cannot have a different pressure there and a different pressure here. Pressure has to be the same across the jet boundary. It is a free jet, right. So, it makes perfect physical sense to assume P3 to be P ambient. Here I cannot do this because this fluid, first of all, is not going to be directly exposed to the ambient. The shock wave impinges upon the jet boundary, and then it is going to be reflected in some manner, right. That means this part of the fluid is isolated from the ambient. So, this can be at a different pressure, ambient can be at a different pressure, which is why P4 is not equal to ambient pressure. Okay. So, the reflection of the shock wave from this type of boundary is something that we will do in the next chapter, okay, from a constant pressure boundary. But we can calculate flow properties at region 4 to a reasonable level of accuracy within the framework that we are dealing with. Okay. Turns out to be very close to 2D results. If you do 2D calculations, it turns out to be very close to the 2D results. So, I know beta 3, I know M3. Remember, M3 is equal to 2.04. So, Mn3 is equal to M3 sin beta 3. Notice that this Mn3 is not the same Mn3 that we calculated before. When we were doing calculations for region 3, we got an Mn3 from normal shock table for going across this shock wave. But that Mn3 is a different value from this Mn3 because the angles have changed now. So, this is the Mn3 that this wave is going to see, or the normal Mach number approaching this shock wave. Okay. So, this is equal to 1.4225. So, now we go to the normal shock table. From normal shock table, for Mn3 equal to 1.4225. Remember, we are now going to the normal shock table with this value of Mach number. In the normal shock table, this would correspond to M1. Okay, this would correspond to M1 in the normal shock table. So, for this value of Mn3, we can retrieve the static properties and Mn4. So, we get Mn4 equal to 0.73 and P4 over P3 is equal to 2.2024 and T4 over T3 is equal to 1.27085, which allows me to calculate P4 as 220.24 kilopascal and T4 as 208 Kelvin. And since I know T4 and T04, since T04 is equal to 300 Kelvin and T4 is also known, I can get M4 as from the following relationship: T04 over T4 is equal to 1 plus gamma minus 1 over 2 times M4 square, which gives me M4 as 1.48. And now I can calculate P04 is equal to P04 over P4 times P4, and the first number I can get from isentropic table 3.56649 times P4 is 220.24 kilopascal. So this comes out to be 785.48 kilopascal. Okay. So this I have obtained from isentropic table for a Mach number M4 equal to 1.48. Okay. So stagnation pressure is also known. Only thing we need to calculate is theta, since M4 is equal to Mn4 divided by sine beta 3 minus theta 3. I can get all the quantities are known, M4 is known, Mn4 is known, beta 3 is also known. We can get theta 3 to be 14.6834 degrees. So what this shows is the following. First of all, you can see that the pressure is not equal to the ambient pressure. It is in fact more than twice the ambient pressure, first of all. So what has happened is, when we went from region 2 to region 3, we compressed it to the correct value. Then because the shock comes through, now it is over compressed. So what do we have to do to equilibrate with the ambient now? So we have to have expansion fans, right? So that is something we will discuss in the next chapter. We will continue the solution once more to see. But what happens is, you get this alternate compression, expansion, compression, expansion for a few nozzle diameters or exit diameters, and then eventually the jet becomes equilibrated with the atmosphere. In fact, this alternate compression expansion is usually called a shock diamond, and I will show pictures of this shock diamond later on. So you get these alternating shock waves and expansion fans and so on for several nozzle exit diameters. The other thing that you should note is your suggestion that we should take theta 3 to be equal to theta 2. Notice that theta 3 here has turned out to be more than theta 2, which means that after the flow goes through this, now it is actually deflected this way by 3 degrees. So from this theta to 11 point something degree would have brought me to the horizontal. Now I have over corrected, so I have gone to this side, which means I need to do something to bring it back. But it is not the velocity that I want horizontal, I want the pressure to be equalized. Okay, that is the most important consideration. And if you actually do a full two-dimensional calculation, you will notice that the results you get are almost identical to what this theory, simple theory, predicts. Yeah.
Flow through the center line. Actually, there cannot be any flow deflection.
Correct.
So that means
what's happening is, within the framework of this theory, if you go through the center line, this shock wave is trying to deflect the flow this way. The other one tries to deflect the flow this way, so that it goes through without any problem. But what can happen in some of these situations is, this interaction is a little bit complicated. So entropy change for the fluid that goes through this may not exactly be the same as the entropy change for the fluid that goes through these two. So you will get something called a slip line. So the flow is slightly more complicated than what we have sketched. But the complications are very small, and most of the times for engineering applications they are really not that relevant. Most of the quantities that we are predicting here will be almost the same as what you get from a much more complicated calculation. But the actual theory, what the theory would predict, a complex theory would predict, is when these two shocks impinge upon each other like this, the theory predicts that this one will reflect from that shock and this one will reflect from that shock. So the angles will be different, slightly different. So this shock does not go through the other one, they do not go through each other. So the first one reflects from that point, the second one reflects from that point. So there can be a slight difference between the two, but the difference is very small, and this theory is actually so simple, it allows us good estimates of these types of quantities. Okay? We will continue this example when we go to the next chapter and talk about expansion fans. Okay? So we will take up a next another worked example which will illustrate similar kinds of things. Probably what is most important about these examples is the calculation of the theta and the beta. Okay? Always remember that these angles are calculated with respect to the velocity vector which approaches the shock wave or ahead of the shock wave. So we will do another example which is also something which is used in many applications, and then see how these calculations can be done. The next worked example looks at something called a mixed compression supersonic intake for maybe a ramjet engine. So you notice that there are two things here, one is called the ramp, the other one is called the cowl. So the free stream approaches the intake this way, and notice that when the free stream comes here, there is one deflection of the supersonic flow here. So the free stream is at a supersonic Mach number, there is one deflection of the supersonic flow by this part of the ramp which triggers an oblique shock like this, and there is a further deflection of the supersonic flow here which decelerates and compresses the flow further. So there is another oblique shock that comes from this corner which further, as I said, decelerates and compresses, and then the flow enters here. Normally there would be a normal shock which stands just here normally, but for our problem, for this particular problem, we are not worried about that. So this is called a mixed compression intake because the flow is compressed externally and also compressed internally in a passage here. Okay, so we will see details of this later on when we talk about supersonic intakes. For now, this is the mixed compression intake that we are going to work with, and let us see what the problem statement says. This is the geometry. Let us see what the problem statement says. The intake shown in the figure is designed for operation at m infinity equal to 3, p infinity equal to 15 kilopascal and t infinity equal to 135 Kelvin. The ramp angles are 15 degrees and 30 degrees respectively. For the critical mode of operation, determine the mass flow rate through the intake, cross-sectional area at the beginning of internal compression and the total pressure recovery. Okay, so for the critical mode of operation. So let us write it down. M infinity, free stream Mach number, is given to be 3, P infinity is given to be 15 kilopascal and T infinity is given to be 135 Kelvin. A critical mode of operation refers to a situation when the incident shocks, as shown in this figure, the two oblique shocks are focused onto the leading edge of the cowl. So, here you see both this oblique shock and this oblique shock focusing on a common point. So, this is referred to as the critical mode of operation. Okay, so, that is what we are looking at now. Okay, so, that is the critical mode of operation that we are looking at. Now, we have also shown the capture area of the free stream tube that enters the intake. Notice that if you take any streamline from here, this oblique shock vector has a direction which goes like this. So, flow comes like this, is deflected towards the shock wave like this, then it goes here, it is deflected further towards the shock wave like this, and then it enters the intake. Okay. What I have sketched here in grey is the capture stream tube. So, you can see that the area of the capture stream tube for unit width in the direction normal to the plane of the board, I can calculate the area of the free stream capture tube, capture area of the free stream. Okay. So, let us go ahead and calculate it. So, from the given dimension, from the figure, the capture area can be evaluated as A infinity equal to 0.0375, assuming unit width in the normal direction. So, it is 0.0375 times 1. So, captured mass flow rate m dot can be evaluated as rho infinity u infinity times A infinity, and if I write this as P infinity over R times T infinity, and this as m infinity times square root of gamma R T infinity, and this as A infinity. I know all the quantities P infinity, T infinity, m infinity, A infinity, everything is known. I can evaluate this as 10.11 kilogram per second for unit width normal to the board. So, let us make a sketch of the flow situation. So, we have this is the first shock, this is the second shock. So, we are labeling this region as infinity. So, this is how the velocity vector looks like ahead of this shock wave. The direction in this shock wave is like this, the direction in this shock wave is like this. So, we call this region 1 and we call this region 2, right. So, this is the cowl which starts from there. And the angles are given to be 15 degrees here for this theta and another 15 degrees here. I am sorry, that is 30 degrees, thank you, that is 30 degrees. I am getting ahead of myself, that is 30 degrees. So, for the first oblique shock, m infinity is equal to 3, theta infinity is equal to 15 degrees, and from the oblique shock table, this tells me that beta infinity is equal to 32.32 degrees from the theta beta m relation, or from the oblique shock table we get this to be 32.32 degrees. Therefore, mn infinity is equal to m infinity sin beta infinity, which comes out to be 1.6. So, we now go to the normal shock table with this value of m1. So, from normal shock table, for mn infinity equal to 1.6, remember this becomes m1 when I go to the normal shock table. So, we retrieve the values from the normal shock table. So, we get P1 over P infinity to be 2.82, T1 over T infinity to be 1.38797, and we get mn1 to be 0.668437. So, the flow upon passing through this shock wave is deflected through an angle of 15 degrees towards the shock wave, and we have obtained these quantities. So, once I know theta and beta, I can calculate, for example, m2 is equal to m1 equal to mn1 divided by sin beta 1 minus theta 1, and this I can calculate as 2.245. So, the Mach number went from m infinity 3 to m1 equal to 2.245. So, for the second oblique shock wave, m1, the Mach number approaching the shock wave, m1 is 2.245, and what about the flow deflection angle through this shock wave? Remember, this velocity vector is like this, and the ramp angle is 30 degrees. Okay. So, as you can see from here, the flow deflection angle, what is the flow deflection angle going to be for this case? 15 degrees, right? 15 degrees from here, it is deflected further this way, it is already deflected 15 degrees. So, that means it is going to be deflected another 15 degrees. So, that means theta 1 is equal to 15 degrees. So, let me be explicit. The choice of numbers is little bit unfortunate. So, let me be explicit and say that this is 30 minus 15 equal to 15 degrees. Okay. Had this angle been, let us say 45, then this would have been 45 minus 15, 30. It seems that I did not choose this number wisely, so it is just coming out to be 15 again. Okay, that is a coincidence. So, we know these values. So, from the theta beta m relationship, I can get beta 2 for this shock wave. We have already had beta 1. Oh, we have already had theta 1 also, right, or theta infinity and theta 1. We have beta infinity. So, that means this angle is going to be, I am sorry, this is beta infinity minus theta infinity, right? This is beta infinity minus theta infinity. Please change that. So, now we have beta 1. So, beta 1 comes out to be 40 degrees. 40 degrees. Now Mn 1 for the second oblique shock wave. For the second oblique shock wave, Mn1 is equal to m1 times sine beta 1, and so this comes out to be 1.443. So when you do these calculations on your own, you must be very careful about the notation. Okay? Remember, Mn1 for the second shock wave is this, whereas Mn1 from the previous one was calculated from the normal shock table. The two are not the same. Okay? This Mn1 we obtained from the normal shock table post the first oblique shock. This is Mn1 pre the second oblique shock. Okay, which means it has to be calculated like this. So when you do these kinds of calculations, you must be very clear about the terminology, the notation, and how you calculate these quantities. Okay, I do not wish to use a different notation for this, that will be very confusing. I do not want to do that. So you must understand how we are calculating these numbers. That is why I am writing all these things explicitly. So now from normal shock table, for Mn1 equal to 1.443. So now this becomes M1 when I go into the normal shock table. I get Mn2 to be 0.723451, P2 over P1 to be 2.25253, and T3 over T2, T2 over T1 to be 1.28066. So we have retrieved the static quantities and the normal component of Mach number downstream of this oblique shock wave from the normal shock table. Therefore, M2 is equal to Mn2 divided by sine beta 1 minus theta 1, and this can be evaluated as 1.712. So the Mach number went from a free stream value of 3 to a value of 2.245 after the first oblique shock wave, and then to 1.712 after the second oblique shock wave. Okay. Now as you can see, now we are ready to compress this using a normal shock. The Mach number has dropped below 1, which is why usually you will have a terminal normal shock standing at the entrance to the intake, which will complete this compression process. 1.7 is low enough that I can compress with normal shock. It is not only effective but also efficient at such low Mach numbers. Below 2, 1.7 is okay, so I can do that. So that is the intent of all these supersonic intakes, to decelerate from free stream value to a value below 2 through a series of oblique shock waves. And I get my P3 to be, now I have P3 over P1, P2 over P1, so I can evaluate P2 as 95.282 kilopascal, and my T2 to be 240 Kelvin. We are also asked to calculate the pressure recovery at the end of the internal compression process. So P03 or P02 over P0 infinity is equal to P02 over P2 times P2 over P1. So we are looking for P02 over P0 infinity. So we do P02 over P2 times P2 over P1 times P01 over and one more, correct? Huh? Did I do this correctly? Yeah, P2 over P1, yeah, times, let me do it like this, yeah, times here times, now this is P1 over P infinity times I am sorry, yeah, P infinity divided by P0 infinity, thank you. So, I can substitute these values, we have all these values and calculate this quantity. This can be obtained from isentropic table, this can also be obtained from isentropic table. These two values we have already calculated using normal shock table. So, the internal pressure recovery, the stagnation pressure recovery can be calculated. Usually it will be a number which is around 80 or so, 80% or so for this, maybe slightly less than that. Okay. One more thing that we are asked is to calculate the area, cross sectional area at the end of the external compression process. This we calculate by looking at the mass flow rate and equating the mass flow rate at this section to the free stream capture mass flow rate. So, let us go ahead and finish the example. So, m dot at the entry to the internal compression is rho 2 times U2 times A2, and rho 2 once again can be written as P2 over RT2, and this can be written as m2 times square root of gamma RT2 times A2. M dot is the same as the capture mass flow rate. So, m dot is equal to 10 kg per second. So, from this I know all the values, I can calculate my area to be 0.01379 meter square. Okay. So, that completes the second worked example. So, we move on to the next topic. Which is detached shocks. So, all the solutions that we have looked at so far are attached shock solutions. In reality, as we said earlier, when theta flow deflection angle is greater than theta max for that particular Mach number, the shock becomes detached. So, obtaining a solution for this case is very complex, and because the flow is much more complicated than what we are assuming, but we can still draw some useful inferences based on the theory that we have discussed so far. Okay. So, let us look at flow over a wedge. So, let us say that we have a wedge with a semi-vertex angle theta like this. So, this is also theta, and let us say that supersonic flow approaches the wedge. If the value of theta that we have shown here, if this is less than theta max corresponding to the free stream Mach number, then we have two oblique shocks, one on the top surface and another one on the bottom surface, which deflects the flow like this, and then the flow flows along the wedge. This is a wedge. Remember, the reason why I keep emphasizing this is not a cone. Although this may look like a cut section of a cone is 3-dimensional. So 3-dimensional effects are much more in a cone, whereas a wedge is a 2-dimensional object which just goes like this. So what we are seeing here is flow over a wedge and not a cone. Although there are similarities, but they are really different. Now what happens when I increase this theta to a value above theta max corresponding to this Mach number? Okay, that is when the shock becomes detached, and in the case of a body like this is usually referred to as a bluff body. Okay, so keeping a bluff body in a supersonic flow many times will cause the shock to be detached and it stands in ahead of the bluff body. So let us say that theta now is like this, greater than theta max corresponding to the free stream Mach number, which remains the same. So in this case the oblique shock becomes detached and it stands in front of the bluff body like this. Like this. Okay. So this is a detached shock, and the standoff distance, meaning the distance between the apex of the bluff body and the shock wave depends upon the angle, how much more than theta max this is. If it is only slightly more than theta max, then the standoff distance will be very small. As it increases, the standoff distance also increases. This is extremely important in many applications, especially in re-entry flows. When the space shuttle or any other craft re-enters the atmosphere, there is usually a very strong bow shock. This is called a bow shock. Okay? There is usually a very strong bow shock which stands in front of the vehicle and creates a lot of problems. Okay? Of course, the space shuttle will be a blunt object at the Mach numbers at which it is traveling, so you have something like this. We can get some idea about the nature of the flow behind the shock wave and the bow shock itself from the theory that we have discussed so far. These are going to be only qualitative inferences, not quantitative calculations. You can infer certain things qualitatively based on what we have discussed so far. Okay? If you look at the flow, right, so the flow is approaching like this. Notice that for the flow along the center line, what is the flow deflection angle? Just across the shock wave, 0. Now far away from the object, where the free stream does not even know that there is such an object, what is the flow deflection angle? 0. So the flow deflection angle is 0 here, and we can easily infer that it reaches a maximum somewhere here. It increases, reaches a maximum, and then again decreases to 0 far away from the object. That is theta. Okay? And then let us look at the strength of the shock wave at each location like this. Okay? Here we can infer that the strength is going to be the highest here, and then far away from here, where the free stream does not even know that there is an object, there is no loss of stagnation pressure. It just proceeds as it is, which means that the strength of the shock wave far away, as I move along this, far away from here, the strength of the shock wave is 0. That means it has become almost an acoustic wave, isentropic compression wave. So the strength increases monotonically from a maximum here and becomes 0, or loss of stagnation pressure is a maximum here and becomes 0 as I approach this end. So the flow deflection angle 0 reaches a maximum, again becomes 0, reduces, and the loss of stagnation pressure maximum decreases monotonically to 0. So this suggests to me that what I am seeing here is the following. If I draw the theta beta m curve corresponding to this Mach number. Remember, this is for an attached shock solution. This is a detached shock wave. So, our inferences for that reason are going to be only qualitative. What this suggests to me, there are two things that we have said, right, and we can actually infer from here to here based on the two things that we have discussed so far. We will pick it up in the next class and then continue from there.